Is it possible to build your own battery pack? And if so, is it even cost-effective? Earlier this year, I built this DIY one-wheel, and one of the things that surprised me the most while building it was the cost of the battery pack. Now granted, the battery pack that I bought is a 20 amp hour battery, and at 48 volts, that's almost 1 kilowatt hour of capacity. It also came with the charger, but still this thing cost about $340, which is about half the price of the overall cost of the project. Hi everyone, my name is Zach, and today I'm going to be making my own lithium battery pack. I feel like I need to give a disclaimer. Building your own LiPo battery pack can be very dangerous if you're not sure what you're doing. Do not attempt this project unless you have a solid understanding of electronics and that you feel comfortable taking on such a project. With that out of the way, let's get started for building a battery pack. You're obviously going to need some battery cells. So for this build, I'm going to be using a very common lithium battery cell called the 18650. It's called the 18650 because of the dimensions of the battery. It's 18 millimeters in diameter and 65 millimeters long. These batteries are found everywhere from laptop batteries to drill batteries and even in Tesla electric vehicles. Each battery cell has a voltage of 3.7 volts nominal and a capacity of 2500 milliamp hours. Now before we go any further, let me explain what nominal voltage actually means, because this is something a lot of beginners get confused about. The nominal voltage of 3.7 volts is simply the average voltage that the cell sits at during a discharge cycle. When a lithium-ion cell is fully charged, it actually sits at around 4.2 volts, and when it is fully discharged, it should never go below 2.5 to 3 volts. Going below that lower cutoff, voltage can permanently damage the cell and cause it to swell or become unstable. This is why a battery management system is so critical, and we will get into that later. I want to make my battery pack 48 volts. So how do I get from 3.7 up to 48? Well, I need to connect 13 of these batteries in series. When you connect batteries in series, their voltages add up. So 13 cells multiplied by 3.7 volts gives us 48.1 volts. Nominal and at full charge, that would be 13 multiplied by 4.2 volts, which equals 54.6 volts. This is actually the standard voltage range used across many electric bikes, e-scooters, and electric skateboards. So if you ever see a product labeled as 48 volt, you now know exactly what is happening inside it. Now, just like any other AA or AA battery, these have a negative terminal and a positive terminal. They're a lot harder to see because these don't have the button on top like a AA or AA, but they are marked here on the outside. And so it's really important to keep those straight as you're connecting up, because if you do this wrong again, it will result in a short and an explosion and a fire. And we want to avoid that at all costs. The first problem we kind of need to overcome is how to hold all of these cells and orient them in the right way. Luckily, to help with that, they make these little battery clips that are designed to hold 18650 battery cells, and they're actually modular, so you can snap more of them together and kind of custom build the size and shape of your battery. I'm going to start by making a grid of 13 by 4. Because I have these cells alternating, I can connect them in series pretty simply by just bridging this gap here, then it'll go down. Bridge the gap underneath, then come up, bridge the gap on top, and so on. And that will allow me to put all 13 of these in series to make a good solid electrical connection. I'm going to be spot welding some nickel strips across these battery cells. You might be asking yourself why I made a grid of 4 by 13 if I'm only going to be using 13 cells. Well, if I just use the 13 cell, that would give me 48 volts, but my battery capacity would only be 2.5 amp hours. I want to make a battery pack with more capacity than that, so I'm going to make 3 more sets of 13 cells. And I'm going to connect all of those in parallel to give me a total capacity of 10 amp hours. That is about half the capacity of the battery that's in my one wheel. Here is something really important to understand about series versus parallel connections. And it is the foundation of all battery pack design. When you connect cells in series, the voltages add together, but the total capacity stays the same as a single cell. When you connect cells in parallel, the capacity multiplies by the number of cells, but the voltage stays the same as a single cell. So by combining both methods, using a 13 series 4 parallel configuration, we get the high voltage we need for our application. And we also get 4 times the capacity of a single cell in the DIY electric vehicle and robotics community. You will see this written as 13SF4P, and once you understand what it means, you can read the spec of almost any DIY battery pack and immediately know both its voltage and its capacity. You can order this nickel strip material just in individual strips like this. But because I'm going to be doing a lot of these cells in series, I went ahead and I bought this type of nickel strip, which makes that job a lot easier. I'm going to make a whole bunch of pieces out of this material and cut them to the right length. Once I'm done with that, it'll be time to start spot welding these pieces onto the battery pack. For that, I'm going to use this cheap battery spot welder that I found on Amazon. To be honest, this was pretty cheap compared to the other professional options. And so I was pretty skeptical. But I've tested it out. It seems to work just fine. If you were going to do this professionally, I would obviously get something that's professional quality, but if you're just going to be making these for fun, this is a good option to go for. Now, let me explain why we use spot welding instead of soldering to connect the cells together, because this is one of the most important safety decisions in the entire build. When you use a soldering iron on a lithium battery cell, you're applying sustained heat to the cell for several seconds at a time. This prolonged heat input can damage the internal chemistry of the cell, reduce its capacity permanently, and in worst-case scenarios trigger something called thermal runaway. Thermal runaway is a dangerous chain reaction where rising heat causes further chemical reactions, which generate even more heat until the cell vents, ignites, or explodes. Spot welding creates an electrical connection in a tiny fraction of a second, so the amount of heat that actually enters the cell is almost negligible. This is why every single professional battery manufacturer uses resistance spot welding for cell interconnects, and why any serious DIY builder should do exactly the same now that I've got the batteries assembled in the plastic clips. It's time to start spot welding those nickel strips in place. Like I said earlier, there are 13 cells in series, and then there are going to be 4 of those in parallel. So this is a 13S4P battery. I'm going to leave this last little tab unwelded for now, and I'll come back later and finish it off. That's because I'm going to be using a battery management system, and I need to solder balance leads to each one of these terminals. And I don't want a lot of that heat from the soldering iron to go into these lithium-ion batteries, because that would be really bad. So I'm going to leave this last one loose, and I'm going to come in and solder that balance lead on there and then tack it into place that way. I avoid getting too much heat on those batteries. At this point, I have all of the nickel strips spot welded to the battery pack, and I've checked the voltages at each node, and I get the voltages that I'm expecting right now. I could connect wires to the positive and negative ends of the battery and use it. But in order to charge this effectively, I want to add what's called a battery management system. A battery management system like this will add a lot of safety features like over-discharge and over-voltage protection, as well as making sure that when you charge the batteries, all of the cells get balanced properly. Let me go deeper on what a battery management system actually does, because it is one of the most important and misunderstood components in any lithium battery pack. A BEMS monitors every single series group of cells in your pack individually. These are called cell groups. And in a 13S pack, like this one, there are 13 separate cell groups. The BEMS watches the voltage of each group constantly. If any one group rises too high during charging, the BEMS will interrupt the charge current to prevent overcharging, which is a leading cause of lithium fires. If any group drops too low during use, the BEMS cuts off the discharge current to prevent deep discharge, which permanently destroys cells. The balancing function is equally important. Over time, cells naturally drift apart in voltage, even when they started out identical. This happens because of small differences in internal chemistry and internal resistance between cells. If you do not balance your pack over many charge cycles, those voltage differences grow larger until your weakest cell group becomes the bottleneck for the entire pack. The BM solves this by either bleeding off charge from the higher groups through a small resistor called passive balancing, or redirecting that excess energy into lower cell groups called active balancing. Most affordable BM's boards use passive balancing, and for the vast majority of DIY projects, that is more than adequate. Can I be honest with you? It's getting to the point where my heartbeat is starting to pick up a little bit. I'm like hyper cautious about where everything is and where all of the terminals are, and making sure that nothing shorts out. Because I'm going to be honest, if there's like a piece of wire or something on my workbench and it shorts it out, that's not going to be good. That's going to be pretty scary. So forgive me if I start to slow down and take my time with this, because I really don't want a fire in here. Now that I've got the balance lead soldered onto the battery pack, it's time to install the BM's board itself. But before I do that, I need to solder on a couple of wires to this board first. I'm going to solder a big 10-gauge wire to the discharge port on this BMS system. This is the connector that I'm going to use to actually power the load, and whatever project that I use this in. So I want it to be a big gauge wire. Gauge is something that many beginners underestimate, but it is critically important. The thinner a wire is, the higher its electrical resistance, and the more heat it generates. When current flows through it at the high currents that are typical in electric vehicle and power tool applications, a wire that is too thin can heat up enough to melt through its plastic insulation, creating a short circuit or starting a fire. As a general rule, you should always size your wires for the maximum current you expect to draw, and then go at least 1 gauge size thicker than that for an extra margin of safety. It is always better to use a wire that is slightly too large than one that is even slightly too small. The second wire that I need to solder onto this BM's board is the charging cable. The charging wire doesn't need to be as big of a gauge as the discharge one because the current is much lower. When you charge the battery, and finally, I'm going to solder the negative terminal of the battery to this board, completing everything. Once I do that, I'm going to add this XT60 connector for the discharge cable and the Dean's connector for the charging cable. This is just the standard that I've kind of come up with. It's the one that I used on my one wheel, so I'm going to continue to do that for this battery. I want to be able to put some sort of insulating layer around each of the lithium cells. So I went to the store and I found this little piece of craft foam. But this was kind of expensive. It's only a single sheet. It was like $3 or $4, and it's not very thick. So I actually went to the hardware store and kind of started looking around the aisles. And I came across this. This is sort of a thicker rubber, and it's used to line the inside of cabinets. And it was like 18 inches by 4 feet. And it was like $8 for this giant roll. So this is what I'm going to use to wrap around the battery to keep it protected and also keep an insulating layer around it. Wrapping and protecting your completed battery pack is more important than most first-time builders realize. Each 118/650 cell has a thin plastic sleeve called a wrapper, and if that wrapper gets torn, scratched, or punctured, it can expose the metal body of the cell, creating a direct short circuit. The rubber padding we are adding here provides physical protection against bumps, impacts, and vibrations that the pack will experience during use. It also prevents any stray piece of metal from accidentally bridging across 2 exposed terminals. Once you have your insulation in place, you can finish the entire pack with heat. Shrink tubing, which holds everything tightly together, gives it that clean professional appearance and adds an important final layer of electrical protection. So at this point, the battery is pretty much done. It's ready to go. I like how it turned out. I love the little blue shrink wrap on the outside. It makes it look very professional. The last thing to do is to test this thing out on my one wheel to see if it works. I'm going to go ahead and swap out the old battery and put in this new one. See if it works. I'm going to turn on the power button here. I'm looking at my voltage meter here and it's reading at 35%, which means that these cells are not fully charged, which makes sense because that wouldn't be safe to sell them and ship them in the fully charged state. So I'm not really worried about that, so this is ready to go. I think if I press down on the foot pad and then lean forward, it should start going. Yep, there it goes, cool. It works. Knowing that this battery works is awesome, because it means I can use this in future projects. It also gives me the confidence to build more of these as I need them in the future. So, the last thing I need to talk about is the cost of this. Was it cheaper to build my own? Now, obviously, I built a battery that's only half the size of the one that I bought for the one wheel. But I ran the numbers and I created a bill of materials. And if I was to build one with the same specs as the one that I bought, it would cost about $270, as opposed to $340. That's like a 20% savings if you're only ever going to need one of these batteries. It's probably better off just to buy one. But if you're going to be building projects that require lots of different batteries, it's probably wise to invest in the tools and the materials to build your own.